Next up, we have Dr. June Stevens.
All right, and Joanne has promised me my full 25 minutes, so prepare yourself. Today I'm going to talk about the development of equations that use anthropometrics to predict percent body fat that are nationally representative, and about the external validation of those equations, equations that include bioelectric impedance, and then the prediction of fat-free body mass, which is fat-free mass, which is what is really of most interest to those of you who are interested in sarcopenia. So I'm going to relate estimation of this back to all of this work done here, and then talk about applications of this to large cohorts. Now, there have been created a lot of prediction equations that include anthropometric measures to provide a practical way to estimate percent body fat. And these have been out for a long time. I'm sure all of you have come in contact with them. The issue is that it's often not feasible to collect DEXA scans or other kinds of more complicated and invasive measurements, and therefore we can resort to having these equations that let us use anthropometric measurements to predict percent body fat and get an estimate in that way. And as you well know, it is a challenge to epidemiologists in cancer who often need very large cohorts to be able to include those other types of measures that are more expensive, and so this offers an alternative. The equations that are out there, though, most of them have been developed in pretty small samples. A lot of times those samples aren't really based on any larger population, so their generalizability is small or questionable. If they used NHANES data, they only used a few of the variables that were available, and they also have other methodologic issues often that I'm not going to go into today. So we aimed to create and test gender-specific equations for use in adults to estimate percent body fat in a diverse, nationally representative sample. And I'm going to tell you that at this late in the afternoon, I'm going to mercilessly drag you through a whole bunch of methods. And the reason I'm doing that is that I want to convince you that after all these years, you're going to switch from those old equations to these new equations. And in order to do that, you need to see all the work that we did to develop them, which could be a problem. I don't know what this is. Okay, all right. And I will just note here that this work was published last year, and you can read it there. So we used some novel analytic methods, at least novel, to this problem. So the data that we used for this project was from NHANES, and we started out with a little over 31,000 participants. We ended up having 10% exclusions, and therefore we passed over 10% of the participants were excluded, I'm sorry. So we exceeded the guidelines that NCHS has put out to indicate whether or not your sample is still going to be representative of the U.S. population. And so we calculated and applied new sampling weights to the NHANES data so that our equations were, in the end, generalizable to the NHANES population, or to the American population. So the analytic steps that we used were to create the equations in a random sample of 3/4 of the data that was chosen at random, and then validate the formulas in the remaining quarter of the data, and then run the final models in the full data set in order to have the full data there to use to calculate the final coefficients. And so DEXA was our outcome variable from the percent body fat from DEXA using full body scans. And then we present to our models anthropometric and demographic variables for selection, and the models select variables and calculate coefficients. So this is the general setup of how one goes about making these models for prediction of percent body fat. But we used a different approach than what had been used previously by using the lasso to do this data selection. We did several pilot studies before we chose this method. I'm not going to show you the results of those, but I will say that the lasso was superior. We also liked it because it's available in SAS software, which is what we like to use. It can handle a very large number of terms in the equation. I think it's quite remarkable. You can have more terms than you have people in the data set, and it's still valid, so that's a really nice thing. It accommodates sampling weights, which you know if you're dealing with NHANES, you got to deal with sampling weights. And it is economic in computational time, which keeps your programmer happy. We presented several candidate variables. There were demographic variables and menarche status in females. And then we had these candidate anthropometric variables. So these were the variables that were available to us in the NHANES data. So we used all of these. And then we had several candidate terms. So in this talk, I'm going to use these two words, variables, to refer to things like these, and terms to refer to mathematical forms that you could use. So for each one of these anthropometrics, we use them in our models in all of these different mathematical forms. So our largest model selected from, over 1,300 terms in the model that were presented to the lasso to choose the equation that had the best fit. Now, you may be worrying that with all those variables, we could do overfitting. This slide here represents the problem of overfitting, but we set several decision rules in order to avoid overfitting and made comparisons between our fitting fitting data and then the data that were reserved for validation to make sure that we didn't overfit. So now for the results of this part. Here we have the equations that we used in, and you can see these are the results in males. The models here are all lettered. You're going to see these letters in some future slides. I don't expect you to remember which one's what, but just that I'm using letters. We had base variables, which you see here, that were in all the models, and then here you can see the anthropometric measurements. We tried to choose combinations of anthropometric measurements that would be probably available to people like you in different studies, or that you might be able to collect in different studies. But I will tell you, if you have a very rich data set that has outcomes and variables you want, and you have anthropometric measurements, and we didn't do your equation, then you should contact me because we can do more. But here you see the R-square measurements that we got. Down here, you can see this equation had only the base in it, so it had BMI in it, and you're down here in the 0.6 level. I want to tell you that in this population, if you just had BMI alone, in other words, didn't give it all of that long string of terms that I told you about and select and all of that, you were down more at like a 0.5 with just BMI, which is how we usually use BMI, okay? I've got marked in green here the equations that I call the preferred equations, and those tended to perform well, not just in R-square, but on other kinds of tests that we did. And we did look at several different indices. I'm showing you R-square here because it is a statistic that a lot of people are familiar with and relate to. Here's the same type of information in females, so this is the same setup here. And I'm just going to show you this summary slide, which will tell you that the R-squares range from around 0.6 to over 0.8, and a little higher in males than females, maybe because we didn't have hip measurement in NHANES, unfortunately, I don't know. 7 of the 14 equations in each gender we felt performed very strongly with R-squares very close to 0.8 and root mean square errors around 2 to 3. So we asked ourselves the questions, so were these equations sufficient and unbiased across all age groups? And part of that slide that we couldn't read there told you that we used individuals from 8 years of age and older. So, you know, these days you have to take different equations to apply to different people, and this can be very obnoxious if your particular data happens to span those age ranges. So we wanted to have single equations that you could apply across all those age groups. Were they sufficient and unbiased across ethnic groups and across BMI categories? So we went through creating lasso equations in each of these subgroups and comparing those equations to the answer for that subgroup using the equation that we created to apply to the entire sample. And what we found was there was very little difference, and there was no reason to create separate equations in separate subgroups. So that was a nice thing to learn. We also looked at external validation of these equations. So not very many of the equations that are out there have been validated in a totally independent external population, which is, of course, what you really want, because that's what you're actually doing when you use our equations in your work. So what we did was we took several of the equations that have been out there for many years. I know all of you have heard of the Durnan-Wormsley equation and the Slaughter equation. So these equations, and we took a look at them, looked at their external validity, and then also looked at the external validity of the new equations that we had created. I'm just going to point out to you here that I have these here numbered. Again, I don't expect you to remember the numbers, but they're going to be numbered in those future slides. So these are these again are the equations that we developed, which we then tested for external validity. Now, one of the things about external validity is you've got to have a criterion measurement in your external data set, and you've got to have anthropometrics in your external data set, the same ones that are in the equation that you use. And this turns out to be quite limiting. You know, if they did DEXA, a lot of times they didn't do anthropometry and vice versa. So we could not test all of our equations or all the equations in the literature. We had to choose ones that would work. Let's see. So the external data that we used for this purpose, two different data sets. One is called VIM1. These are people who are a subset of the Cardia data set in young adults. And then the FELS data in which spanned both adults and youth. And I should also mention Cardia has African Americans and whites. So this slide shows you the R-square in these external data sets. You see I've got down here the results from VIM1 and the results from FELS. On the left-hand side within each panel are the equations that we developed with the lasso. In the green dots are the ones that I called the preferred equations, and the blue dots are the other. And then in this column to the right are all those other equations I showed you in the literature. And what I want you to get out of this is, you know, I used this criteria of 0.75 here just for you visually to say, okay, did it do pretty well for an external validation? You can see that they did not do as well in the VIM1 white men, but otherwise our preferred equations did pretty well and in general did better than the equations that are from the literature in this external validation. All right, well, I can just talk a minute. So that was looking at the R-square, but we were also really interested in looking at how these equations performed in these subgroups. You know, did they tend to overestimate percent body fat in African Americans versus whites? Did they tend to overestimate in obese people versus underweight people, et cetera? So we looked across subgroups to look at differential error. And this slide, so I'm not going to show you all of that work, but this is just the work across BMI levels to see if there was a differential in the estimation. So what this slide is, I guess I can't use this thing. What this slide is showing is the band across the zero means that there was, zero means there was no difference across the subgroups within that subgroup of the predicted value, the value from the equations versus the gold standard or criterion method. And we're looking to see how that works across within normal weight, within overweight, and within obese. Again, you've got the equations that we developed in the letters and the equations from the literature in the numbers. And we've drawn the band there of what we think is acceptable differences. And you'll see that in general, our equations performed well, and some of the equations in the literature tended to underestimate adiposity in the obese much more than they did in normal weight. And of course, as epidemiologists, we really don't like differential error, right? So this is showing that problem. All right, so this is the results from BIM1, and this was the, I don't know why it's doing this. When I forward the slide, it turns black. All right, this is the data from FELS, trust me. It shows basically the same thing. Okay, so conclusions on external validity. We found our equations tend to perform better than the other equations. That was the kind of the general conclusion. All right, let's talk about equations that use bioelectric impedance. Up to now, I've been talking to you about anthropometry. And this work has also been published. It came out this year. So we used, again, the lasso to develop equations. We could only do this in 8 to 49-year-olds because those were the people that had BIA measurements in Haynes. So we use 3 BIA variables alone or with other variables. So if you're familiar with BIA, you know what you actually get from the BIA machine is reactance and resistance. And we also gave them, you know, for good measure, that what they call impedance variable, which is height squared over resistance. So those are the 3 that I'm talking about as being the BIA variables. And if you use those 3 variables and in all those different terms that I gave you, when you crank it through your lasso, you get extremely low R-squares, okay? So the message is, and I'm just saying that, dwelling on this because some people don't realize it, if you just have BIA measurements, it's terrible as a measurement of body composition. If I then add into the variables for selection, age and race, it's still terrible, okay? And then if I add in addition, I give it height, weight, and BMI, then you're getting R-squares that are pretty decent. But actually, what I'm going to show you now is that we can do better. This is showing the 3 BIA variables alone or with other variables, and I think I'm going to. Now, what you're all wondering is, should I be measuring BIA in my study or should I do skin folds? Now, researchers tend to hate skin folds because they take a lot of training to get people to be able to do them, but they're not so sure whether they want BIA either. So what we decided that would be interesting to do would be to compare what you get with BIA versus skin folds. So that's what this is showing you. So remember, the first line shows you what you get with just the basic variables, which are listed down here at the bottom: age, race, height, weight, and BMI for prediction of percent body fat. Then if you add 2 skin folds, that's triceps and subscapular is what we did here. Then you get up to 0.813 in males. And if you instead were to add the 2 BIA variables, you would get 0.819 in males. So pretty much exactly the same. In females, the skin folds were a little lower than what you got with BIA, 0.80 versus 0.844. And then in both genders, if you added skin folds and BIA, you got a slightly higher R-square. So kind of in summary here, in males we have 16 equations that are produced R-squares greater than 0.83. I didn't show you all this work, but we created those equations, and they're in the publication I pointed to. And the same for females, pretty much. We also looked for bias in the same way that I reported earlier on the equations for anthropometry, and found that it was low for these 16 equations. And when BIA variables were added to equations with demographics and anthropometrics, the performance was consistently improved. The addition of either two skin folds or BIA produced R-squares greater than 0.8, and when BIA variables were added to equations with demographics and anthropometrics, performance was consistently improved. But BIA alone, or with only demographic variables and height, did not successfully estimate percent body fat. So that's your summary. All right, so all this time I've been talking about percent body fat, but what you're really interested in is the kilograms of fat-free mass as one of the variables that you might be able to get with these inexpensive measures. And I wonder how many of you know what the association is, or what the trends are about being able to predict percent body fat versus kilograms fat-free mass. And actually, I had a conversation with John Shepard about this that it inspired me to do some more work on it. So our equations estimate percent body fat, but how successfully could these equations be used to estimate kilograms of fat-free mass? Or do we need to start all over with our lasso and predict fat-free mass kilograms rather than use the equations that we've already predicted for percent body fat? And of course, kilograms of fat-free mass and percent body fat are related to each other in a very simple algebraic way. And I can tell you that in the literature, all the time, they go back and forth between these kilograms of fat-free mass and percent body fat and throw out the R-square and assume it applies all the way up and down the line despite this algebra, which was not necessarily true. So here's the results here of this work. So what I'm showing you here is the lasso-derived equation for percent body fat. We'll just look in males first. And these are the different equations I showed you a minute ago with these either skin folds or reactants or both in them. And this is a lasso-derived kilograms of fat-free mass, okay? Started the whole process over and calculated fat-free mass. Derived a new equation for fat-free mass. In this column are where I took the equation I already had developed for percent body fat, did the simple algebra, and calculated kilograms of fat-free mass. And this is what you find. Kilograms fat-free mass gives you a higher R-square than does percent body fat. So remember this when you're seeing people showing 0.9s and things like that and other papers showing much lower levels. This is consistent in the literature. I've seen this many, many times. I don't entirely understand it, but I'm still working on it. But this is kilograms of fat-free mass can be predicted more precisely than percent body fat, okay? And you can derive kilograms of fat-free mass from a lasso equation for percent body fat, and it performs quite well. As a matter of fact, here it's a little better, but I think this is just rounding error going on here, so I wouldn't take that too seriously. And so you see the same thing in the females as I just showed you here in the males. Okay. Now, let's compare these methods looking against our gold standard, which is, in this case, is DEXA. So for men, the kilograms of fat-free mass was 50.620. If you use a lasso-derived equation, which was specifically derived to predict kilogram fat-free mass, here are the estimates that you get for kilograms fat mass. If you calculate it from percent body fat, here are the estimates that you get. So although the R-squares were very, very spot on, you're getting a little bit of underestimation across the board if you use the equation that was calculated to originally predict percent body fat. And I have in the next slide done the math for you so you can see how different. So these numbers are how different were the estimates calculated in these ways from the actual DEXA value. And you can see if you derived a new lasso equation, the differences were quite small. If you calculated it from the percent body fat equation, the differences were a little larger. But I want to point out that as a percent error, not percentage of body fat, but a percent error of the amount, this is only a 1% error. So you're getting an equivalent R-square and only a 1% error in underestimation in these cases. If you just use the lasso equation that was intended to predict percent body fat and get your kilograms of fat-free mass estimation from that. Gosh, I hope you followed that. It's hard stuff to talk about. Okay. Okay, so conclusions are that anthropometric equations generally predict kilograms of fat-free mass with a higher R-square than they do percent body fat, and equations developed for prediction of percent body fat generally can be used successfully for the prediction of kilograms fat-free mass. And I'm saying generally because it's been this way in our hands. It's what I see in the literature, but my very smart statistician has not been able to derive the math to show that this is always true. So we're still working on it. If you know how to do it, let me know. Okay, so we're here at applications to large cohorts. So the strength of these new equations that we have developed are that they are applicable to ages 8 years and older within genders. They have good performance and low bias in important subgroups. They have been shown to be reasonably externally valid, and the percent body fat equations can be used to estimate kilograms fat-free mass. There's limitations that DEXA measures are not a perfect measure of percent body fat, and unfortunately the NHANES data did not have HIP measurements, and I really would have liked to have had those. Also a problem, but not really a problem, is that the equations are very complex. These are not something you're going to sit down with a pencil and a pad of paper and do. If I gave you the equation, they're long and complicated. But it is that complexity that probably is why they are not biased across these different subgroups, and they do perform well in a very wide range of ages. And so I think that is worth the complexity. And we have provided you with a website, which show the address right here, and it's in our publications. And you can give us a columns of your anthropometric data, and the software will return to you a column of percent body fat. Okay. So actually, we don't return it to you. We give you the software, and you do it. So we don't ever see your data. But anyway, so it's easy to do. I hope you will try it. So this is the real thing I want you to think about. These equations make it possible to leverage existing data to study associations of fat-free mass with disease and other outcomes at low cost. So I agree with Steve that digital images and things like that are going to be very important in our future. But many of you are probably sitting on data sets that you've already got that are really rich in terms of cancer outcomes or other outcomes that you're interested in that have anthropometry. And you might be able to use these equations in order to get an assessment of fat-free mass that's pretty darn decent with data that you've already got in hand. And so that excites me that we might be able to do that. So we hope you will use them. Thank you.